Today I'm going to talk to you about parent functions. Now this terminology comes up a lot in the grade 11 curriculum, and all they're talking about when they say parent function is the most basic of any function. The basic function. A function that hasn't had any transformations done to it. Now again, transformations, and in particular this chapter 1, is so critical for success in the rest of the grade 11 curriculum because it is almost entirely based on transformations of different functions. So it's extremely important that you can graph these 5 basic functions, understand how to do them, know what the domain and range is, and then in a little bit later in this chapter we'll get into transforming some of the more difficult ones. So let's get down to the basic ones, and this goes back to grade 9 math where you learned about the line. Only now we're going to be using function notation as we talked about yesterday. So f at x equals x. Some people say f of x, but I think f at x even makes more sense, right? F at the x value. So if I wanted to draw the line f at x equals x, all I would have to do is plug in different values for 1. So f at 1 would be 1, f at 1 would be 1, f at 2 would be 2, and f at 0, 0, f at minus 1, you get the idea. F at x is a line. F at x equals x is just a straight line that goes right through the origin. Now again, in grade 9 you did all sorts of transformations of these. You didn't know they were called transformations at the time, but you did things like using y equals mx plus b, which is the slope y-intercept form. Again, the slope y-intercept form of the line, and all you did was change the slope and the y-intercept, and you could draw a different line. Let's just put a different line on here as well, just so that you get the idea. This, however, is the parent function. F at x equals x. That's the most basic line you can draw. Notice how nicely it goes 45-degree angle through these two quadrants on a coordinate plane. So let's draw another one just for the fun of it, because you should know how to draw lines by now. So let's say I do y equals minus 2/3 x plus 2. Now again, we go back to our transformation here, or in this case, we're going to look at the y-intercept b. Y-intercept is 2. So that's where I begin to graph my line. You don't need to do a table of values for these. It's quite obvious how you're going to get from 2 to a next point. So your very first point is 2. That's if each one of these is representing 1 unit, obviously. I didn't give the scale. So if I'm at 2 and the slope is minus 2/3. So remember, the top tells you whether or not you go up or down. It's negative, so I'm going to go down 2 and 3 to the right. 1, 2, 3. So I will put another dot there, and there you have it. So there's y equals minus 2/3 equals minus 2/3 x plus 2. Okay, so this, however, though f at x equals x was the parent function, this would be a transformed linear function. So we also want to know here, what is the domain and the range for this function? So let's talk about domain again. We touched on it in the first video. The domain, all that means is what values can I put in for x and get an answer for y, or in this case, f at that value. So if you look on this line here, and notice how I put arrows on the end of it, that means that my line could go on forever. I could put in 100. F at 100 is 100. F at 1 million is a million. F at minus 3,000 is minus 3,000. So this line goes up. It continues forever. To the left, I can put any value in for x this way, and the height, as you can see, it's going to go up and down. So the domain again is, we're going to call it capital D for domain, is the set, that's a squiggly bracket, set of all x's, such that x is an element of real numbers. That means I can put in any value for x. I can use a fraction, I can use a decimal, I could ask you what's f at 3.2, and you'd say 3.2. So that's this equation here. Now, of course, if I was doing this domain and range, the domain is still all x's. I can put in any value for x here and get an answer for y, right? I can do whatever I want. Now the range, I'll put the range here. The range is capital R for range. Note the difference between this R for real numbers and this R. This real numbers, I put 2 bars on the left side here. So my range here, in this case for f at x, it's going to be, the range is f at x instead of y. Remember we just said that f at x means the same thing as y. So I'd say the range is the set of all f at x's such that, in this case, again, you probably guessed it, it's going up forever this way. Now remember, don't just look here because there's arrows on the end. It continues in both directions for forever, as long as you want it to. So f at x is also an element of real numbers, close the bracket. So there's my domain and range of a very basic function, the function f at x equals x, which is a linear function. Linear function. And again, is it a function? Yes, because it passes the vertical line test. If I do vertical lines across either of these lines, I would only intersect it at one point. Okay, so the second function we're going to do is the one you did in grade 10, did a lot of it in grade 10, f at x equals x squared. Now x squared, obviously, this is the most basic function you can have for a quadratic. It has no stretches, compressions, translations, left, right, up, or down. This is the basic function. Now we'll get into a lot of those transformations that I just mentioned in the next section. So for now, we're just going to look at x squared. And if you want, you could do a table of values. Now, some of you may have learned a step pattern for quadratics, which is also a good idea. So I'm going to put x here, and this is going to be f at x. In other words, my x coordinate, my y coordinate. When you're graphing a quadratic function, it's very important to use both positive and negative values. And the reason that is, let's say I'm just going to start it here at 0, and I'm going to fill in these in a minute. But if I went only from 0, if I put in 0 for x here squared, I would get 0. If I put in x is 1, remember you put it in brackets, 1 squared, 1. And if I did 2, 2 squared would be 4. So if I graph that function, it would go 0, 0, 1 and 1, 2 and 1, 2, 3, 4. And you can see that if I only use positive values, that I would only have half of a parabola. In fact, you might not even think this is a quadratic. It could be perhaps an exponential function. If I carried this line just below here, it would go down like this. It could be an exponential function. So it's very important that you go back here and plug in some of the negative values as well. Oh, I left too much space there. That's okay. So when I put in minus 1, remember that it's minus 2 in brackets and square it. I'm squaring both the negative and the 2. So a negative 2 times negative 2 is positive 4. Be careful with your negatives. Remember, when you're substituting in a value for x, you should always plug it in brackets. Minus 1 squared would be 1. So now I have a few more points here. So minus 1 and 1, and minus 2 and positive 4. So now you can see that I have this beautiful parabola, and it's a little bit crooked, but it's not bad. I'm writing on the side. Okay, so here's my function, f at x equals x squared. We'll talk about those transformations of the quadratic later. So the domain and range now. So we're going to write this as a quadratic function. Is it a function? Yes, it is. Because anytime I do a vertical line test, I would only cross at one point. It's a quadratic function. Very familiar to you if you finished grade 10 math. So now we're going to talk about the domain and range of this function. The domain is going to be D, again, curly bracket, the set of all x's such that, so now let's go back. If I look here, what value can I put in for x and get an answer for f at that value? And I'm sure you can see that I can put in any number here that I want. I could put in any negative value, I could put in any decimal value, I can square any value. There's nothing you can't square and get an answer. So the domain here is going to be x is an element of real numbers, just like for linear functions. I can put in any value for x, and I should have labeled my coordinate planes here, x and y. The range for a quadratic is a little more specific because the range said what is the height of this function? Where does a function go on my coordinate plane? So the basic function or parent function of f at x equals x squared starts at 0 and it goes up. So if I took my fancy little ruler here and I covered this, you'd say, oh, there's no function down here at all. So the range has to start where the function starts, which is actually the y coordinate or the f at x value of the vertex. So right here, this point here is 0, 0, happens to be the origin for this function. It starts here and it goes up. And you can see I've put arrows on both sides here, which means the function is continually going up, 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 right off my paper, right out the window. So the range is, in this case, we're using the function notation. So range is f at x, or my y values, if you want to think of it like that, such that f at x has to be greater than or equal to 0. And f at x is an element of real numbers. Now the reason I say that is that if I didn't, I wouldn't be able to join all these dots together, all these specific values. There are values for every little x coordinate along the way here. They all have a certain height. So that's why we say real numbers. If I said natural numbers, you would have a series of dots, right? You wouldn't have anything in between 0 and 1. So that's the quadratic function, and you should know what a quadratic function is if you're in grade 11 math, and the grade 9 curriculum covered the linear functions quite extensively. So let's turn the page here, and we're now going to talk about the square root function. Now this isn't something that you saw in grade 10 math. The equation is f at x is equal to the square root of x. Now, if you have a calculator in front of you and you tried to take the square root of a number that is negative, you wouldn't get an answer. So for all these functions, for f at x, you want to know, okay, well, what happens, what is the lowest number I can put into this equation? This is an equation, a function. What can I put in here and get an answer? So if you put in, let's do a little table of values again. So we're going to have x, and we're going to have the square root of x, which is going to be my f of x. So I know I can't take the square root of a negative number. If you try it on your calculator, it'll give you an error. So I'm going to start at 0. Some people forget that you can take the square root of 0. The square root of 0 is 0. The square root of 1 is 1. Square root function. In other words, what number multiplied by itself will give you 1? The square root of 2, again, that's kind of a messy answer. If you put it into your calculator, it gives you a whole bunch of decimals. It's not so easy to graph here. So we're going to ignore that one and go to something that we can take the square root of nicely. And the closest one, of course, would be 4, because the square root of 4 is 2. The next perfect square, so if you went this way, it might be easier to see. 0 squared is 0, 1 squared is 1, 2 squared is 4. 3 squared would be 9. So that's my x-coordinate is 9 and my y-coordinate is 3. So we're going to start here. We're going to graph it. Here's my y-axis, my x-axis. So 0, 0, 1 and 1, 2, 3, 4, and 2. 5, 6, 7, 8, ooh, just fits. 9, right out here is 3. So I'm going to join all those dots together like this, and there's my function. That's the square root function. So the square root function. So if we had another value under this radical sign, let's say I had something like this. Let's say I have f at x is equal to the square root of x plus 5. Now I have to think about what makes this equal to 0, because that's where the function is going to start, right? Because I can take the square root of 0. So let's say I put in 0 here for x. 0 plus 5 is 5, square root of 5, 2 point something. If I put in minus 1 plus 5 would be 4. The square root of 4 is 2. So I want to know what value for x here is going to make this little equation equal to 0. So I'm going to write it out here for you like this. X plus 5 has to be equal to 0. So that means x is equal to negative 5. So when I put in negative 5 here for this function, negative 5 plus 5 is 0, square root of 0 is 0. So if I was to do a table of values for this little function, I just want to do this quickly because, so I'll put it in, I'll put the function here, maybe that'll help. So if I put in minus 5, the square root of 0 is 0. So what value for x here would give me a height of 1? So I want to make the square root of 1. So if I put in minus 4 plus 5 would be 1, square root of that would be 1. And if I wanted to go one step farther, if I wanted to graph this, now you can see that I would be at 1, 2, 3, 4, 5, and 0. I'm going to do this one in green so it looks different. So I have this one. I have minus 4 and 1. And you can probably guess that if I went over 1, 2, 3, 4, so if I put in minus 1 here, if I do minus 1 plus 5 would be 4, square root of 4 is 2. And I'm going to put that in here. So minus 1 and 2. So here's my other function here. So it's the very same as this one, the very same shape. It's like cut and paste, right? I could make a copy of this and slide it over 5, and that would be this green function here. So I'm just going to put this one in green so you know that that matches this line here. Okay, so let's talk about the domain and range of the parent function. Okay, the domain. What values can I put in for x into this equation? So this is the first time in the first functions that we've done so far that there is a restriction. I can't put in anything for x. I can only put in values that are greater than or equal to 0. So the domain is going to be x's. So x has to be greater than or equal to 0, and x is going to be an element of real numbers. Oops, that was tight. Okay, so for this parent function, the square root of x, this would be the domain. Now, think for a minute, what is the range? The range. So I'm hoping you're looking at the graph and trying to figure that out. Where's the height? What is the height of this function? Oh, I guess we were using function notation, so we should call this f of x. Let's fix that. Okay, so f of x. And if you look at the function, very similarly to the quadratic, it starts here and it goes up. So there's no function below the x-axis. Look, see, there's nothing down there. It's all up here. And how high does it go? Well, if I put in the square root of 100, it would be up to 10, and so on. If I go out farther, this is still going up, 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 a little bit at a time, but consistently on an upward trend. So this means that f of x has to be greater than or equal to 0, and f of x is also an element of real numbers. Now, some teachers don't expect you to write all of this out. You check with your teacher to see what her or his rule is for writing out domain and range. So that's the square root function. Now let's go to probably the hardest one. And we do later on in the textbook get into transformations of this. So when you're finished the lesson, I want you to go back and I want you to go over all of these rules and make sure that you can sketch each one of these functions, that you know where it goes. And from then, when we do the transformations, it will make it so much easier. So 1 over x, this is kind of a difficult function, even just to look at it. 1 over x, fractions, everyone gets freaked out about them. Okay, what can I not put in for this value here? So you should be thinking, well, can I put in any positive number? Yes, I could have a half, a third, a quarter, a fifth, a sixth, a seventh, and so on forever. Can I put in a negative number? Sure, negative 1. 1 over negative 1 is negative 1. 1 over negative 2 is negative a half, and so on. This is only restricted by one thing, and I hope you figured it out. That is the most important rule in mathematics, is that you cannot do what? I hope you're saying it to yourself. You cannot divide by 0. You can't divide by 0. So if you can't divide by 0, you can't put a 0 here. What that means for this function is that it is going to have an asymptote. Now this is, I know you did not learn this in grade 10, and your teacher might be just glossing over this, forgetting that you haven't learned this. It has an asymptote at x equals 0 because I can't use 0. So I'm going to put a dotted line down here. Remembering that vertical lines, if you have a vertical line, if I had a vertical line over here, that would be x equals 2. All the x's are 2 on this line. All the x's are 0 on this line. People get that mixed up all the time. So this is x equals 0. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. See what I mean? All the x's are 0. So that's the asymptote. I can't divide that. So right away, that puts a restriction on my domain. The domain is real numbers, but x can't be equal to 0. And I'm going to write the domain out here first, even though we like to keep that till the end, but we're going to put it here because we figured it out. So the domain is the set of x's such that x is not equal to 0 and x is an element of real numbers. So that means that my function is going to be in these other quadrants somewhere. We haven't defined that yet, but it's going to be in here. And I'm not going to cross this line. You can never cross a vertical asymptote. When you get into higher math, you'll find you can cross horizontal asymptotes, but never a vertical one. Okay, so if x can't be 0, then that means y can never be 0 either. Like, how am I going to make a 0 by dividing by something? You can't divide by something and get 0 for an answer. So that means the range of my function is going to be f at x, such that f at x can't be equal to 0 either. And that means there's another asymptote. So this is a vertical asymptote. Vertical means up and down. And a horizontal asymptote, y equals 0, a horizontal asymptote. Horizontal. So that means I have another asymptote here because I can never divide by something and get 0 for an answer. So the other key points, and it's very important that you get key values like 0, 0, 1, 1, 4, 2. Those are key values on this graph. The key points on here, the most important ones are 1, when x is 1. So when I have x is 1, I have y is 1, right? 1 divided by 1. When x is -1, I get -1. These are two very important points on this graph right here. 1, 1, -1, -1. Okay, these are very, very important points because from there, you're going to be able to sketch this very quickly. Now, pay attention because this is the tricky part. As I go out this way, as I increase my x values, so when x is 2, I would have 1 over 2 is a half. When x is 3, I have a third. When x is 4, I have a quarter. When x is 5, I have a fifth. So it's going down like this. It's getting very close to this axis, but it's never going to touch it or cross it. Think of a really big number. 1 million. 1 over a million as a decimal, 0.000006. Hope I said the right number of zeros. So this gets really close, but it doesn't cross it. So the same thing is going to happen on this side, right? When I put in -2, I would have -1/2, -1/3, -1/4, -1/5. So it's going the same way on this side. And now we have to talk about what happens in here. So this is where people get a little confused because let's say I pick a half, 1 over 2. So what's 1 divided by a half? And you're going to say, oh, I don't know, I'm not very good at fractions. 1 divided by a half. So if I had 1 pi and I cut it in half, how many pieces do I have? Well, you know, the answer would be 2, right? You have 2. So a half goes to 2. Let's go really far down. Let's go 1 divided by 100. 1 divided by 100th. 1 divided by 100th. 100. This is something really, really close to this axis. So 1 divided by 100th, if I divided something into hundredths, I would have 100 pieces. Right? So this is going to go up very quickly like this, and it's not going to cross this vertical asymptote. So let's do a few more values on this side to show you that it's the same thing over here because we're dealing with fractions, right? Between here and here. Those are where we're using fractions. Fractions. Ooh, fractions. Okay, so let's go in here. Let's say, what's 1 divided by -1/10? I'm hoping you've got this figured out. Look, when you divide by fractions, you invert and multiply. So that's the same. Maybe it's easier if I read it this way. 1 divided by -1/10. 1 divided by -1/10 is 1 times -10 over 1, which is -10. Right? So 1/10 -10. It's not even on my graph. So all I have to do is start sketching this. These are sketches of functions. There you go. And that is your 1 over x function. Also called the reciprocal function. Let's write that here. Reciprocal function. Reciprocal function, 1 over x. So let's label it f at x equals 1 over x. So it's really important that you understand how to graph this. These key points here, 1, 1, -1, -1, if you know where the asymptotes are, you can sketch this function in 2 seconds. Okay? Now the very last function in this section is the absolute value function. And I know for sure you did not learn this in grade 10. I taught grade 10 many times. And you probably are even wondering what this is supposed to mean. So these are absolute value. It's an absolute value sign. It's not like, well, it's kind of like a bracket, but specific to the absolute value function. So let's write absolute value function. And all it means is it's talking about the distance from the origin. So if I said, what's f at 1? You'd say it's the absolute value of 1. How far am I away from the origin when I'm at 1? And you'd say 1. The absolute value of 1 is 1. If I said, what would f at minus 2 be? So I'm looking for what is the absolute value of minus 2. When I'm at minus 2, how far away from the origin am I? Well, I'm 2 units. So if you notice, your answer is always positive. You don't say the absolute value of negative 2 is negative 2. You're 2 units from the origin. Another way of thinking of that would be like temperature. I said, well, it's minus 10 outside. And you'd say that's 10 degrees away from 0. Right? 10 degrees away, or 2. So in this case, that's all you have to do. So let's make a table of values because this is a really easy graph to do. So I have x, absolute value x, and I'm going to do minus 3. The absolute value of minus 3, I'm sure you've got it figured out now, 3. The absolute value of minus 2, 2. Absolute value of minus 1, 1. Absolute value of 0, 0, 1, 1, 2, 2, and so on. Now you may notice that if you looked here from 0, 0, 1, 1, 2, 2, that looks awfully familiar to, whoops, wrong page, looks very familiar to this function here, right? 0, 0, 1, 1, 2, 2. So the absolute value function is going to have this branch here, and the only thing that's going to be different is on the negative where you have the negative values. So I'm just going to freehand graph this here. Absolute value. I call it the victory function because look what happens. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. It's going up like that. And on this side, minus 1 and 1, minus 2 and 2, minus 3 and 3, minus 4 and 4. And if you get your ruler out, always use a ruler. Make your work neat. It's also nice to use using graph paper when you're graphing, right? So it's going to go like that. It's going to go like this. See, it's the V graph, the victory graph. Nice 45-degree angle up here, 45 degrees through here. So finally, and this very last part of the lesson today, what is the domain? The domain of the absolute value function. Is there anything I can't put in for x? I put in all negative values, all positive values. I even put in a 0. No domain restriction. X is an element of real numbers. Anything I want. The range is a little specific here because look at the graph. Where does it start? Where does it go? It starts at 0 and it goes up. So f at x is greater than or equal to 0. X is an element of real numbers. And there you go. So looking back at the graphs that we've done today, you can see that restrictions on domains only happen when there's some value that doesn't work. So for my x values, linear functions, anything. Quadratic functions, anything. Square root function, whoops, no, there is a restriction because I can't take the square root of a negative number. Can't square root a negative number, right? You can't do that. What can't you do with 1 over x? You cannot divide by 0. So those are things that make restrictions on functions. So I hope I've taught you something today. These functions, I would suggest you go back and you go over them a number of times. Make sure you can sketch them. You can find some critical values that you want to use in order to make the shape of your function, and you'll be off and running. Go practice.